talk of the day by Boban Karapetrovic, who will talk on Hilbert matrix operator on Bergman-type spaces. Boban.
Thank you. First of all, I would like to thank the conference organizers for this invitation and the opportunity to participate in this focus program on analytic function spaces and their applications. And I must especially thank Javad for the invitation to speak on this topic today. So I will talk about Hilbert matrix or Hilbert matrix operator on some classical spaces of holomorphic functions in the unit disk in the complex plane, especially on Bergman and weighted Bergman spaces. That is on the Bergman-type spaces. And we are interested in questions related to the boundness and exact norm of the Hilbert matrix on Bergman-type spaces. And actually, I will give an overview of some well-known and some recent results related to this topic, and mostly without proofs, having in mind the time limit. And also mostly starting from 2000, when actually Siskakis started with this topic. So I can start now. First, some basic definitions, some basic notation. So Hilbert matrix. Hilbert matrix is infinite matrix whose entries are given by 1 over n plus k plus 1. And of course, here n and k go from 0 to infinity. So this is actually Hilbert matrix. And as you can see, anti-diagonals have the same elements. So Hilbert matrix is actually Hankel matrix in more general settings, but today we only consider this particular example of Hankel matrices. So the main object today is this matrix, Hilbert matrix. And next, something related to the Hilbert matrix on some classical sequence spaces, LP spaces. And of course, Hilbert matrix H can be viewed as an operator on sequence spaces. So if we have if we have a complex sequence AN, then Hilbert matrix sends that sequence to the sequence given by this summation. K goes from 0 to infinity, AK over n plus k plus 1. And also for p between 0 and infinity, p can be equal to infinity. We have this standard definition. LP is the space of all complex sequences for which this norm is finite. In this finite case, when p is strictly between 0 and infinity, and when p is equal to infinity, we have this supremum norm. And the following result, well known, very old, belongs to Hardy, I think, dates back around 1925. So we have this theorem: Hilbert matrix H is bounded on LP sequence spaces if and only if P is strictly with between 1 and infinity. And also in this case, we have that norm of Hilbert matrix H on this LP space is equal to this quantity, pi over sinus pi over p. And this can be motivation to consider Hilbert matrix on spaces of holomorphic functions. So first we have this notation standard, hol of D, space of all functions holomorphic in the unit disk D in the complex plane, of course with center at 0. And now, actually, H can be viewed as an operator on spaces of holomorphic functions in the unit disk by its action on the Taylor coefficients. So if we have a function f holomorphic in the unit disk D, given by this Taylor expansion, by this series, then the image of f with the Hilbert matrix is given by this summation. By this summation on the right side, and this right side, it does not always have to converge in the unit disk, of course. So this formula is important for us today. We have action of the Hilbert matrix of some holomorphic function f in the unit disk D. And allow me now to say again definitions of some basic spaces of holomorphic functions in the unit disk in the complex plane very briefly. First, we have integral means of order P. So we have holomorphic function f, P between 0 and infinity. P can be equal to infinity, and radius r between 0 and 1. So we have this integral means or integral mean of order P in this finite case when P is strictly between 0 and infinity. And when P is equal to infinity, we have this supremum or maximum of modulus of function f on this circle with radius r. This immediately implies that the definition of Hardy space HP, the space of all holomorphic function in the unit disk D, for which this node given by this supremum of this integral means is finite. And these integral means, they are increasing functions of this radius r. And a very important definition for us today, the definition of mixed norm space, H, with these parameters P, Q, and alpha. P and Q are between 0 and infinity. And also P and Q can be equal to infinity. Alpha is strictly between 0 and infinity. So this mixed norm space, HPQ alpha, is actually the space of all holomorphic functions f for which this mixed norm is finite. Again, in this finite case, when Q is between 0 and infinity. So here under integral, we have again integral means of order P to the Q, and this way 1 minus R to the Q times alpha minus 1. When Q is equal to infinity, we have the norm given by this supremum. And if we allow alpha to be 0 here, we obtain this norm, the classic Hardy space norm. So if we allow alpha to be 0, then space HP infinity 0 is actually Hardy space HP. And in that context, the spaces HP infinity alpha are known as weighted Hardy space. So this space HP infinity alpha is actually weighted Hardy space. Now we have generalized mixed norm space. Again, function f is holomorphic in the unit disk D with this Taylor expansion. We also have a real number t, and now we can define Hardy-Littlewood fractional derivative of order t of function f given by this series. So this is again, of course, function holomorphic in the unit disk D. So we have this factor m plus 1 to the t. And now generalized mixed norm space H with these parameters p, q, alpha, and t is the space of all holomorphic function f for which this HPQ alpha norm of fractional derivative of order t of function f is finite. So function f belongs to this space HPQ alpha t if and only if this function d to the t of f belongs to this classical mixed norm space HPQ alpha. So we can write immediately that HPQ alpha t is actually d to the minus t now of this mixed norm space HPQ alpha. When t is equal to 0, this generalized mixed norm space HPQ alpha 0 is classical mixed norm space HPQ alpha. And also we have one more important fact here. If again f is holomorphic in the unit disk D, and P and Q are between 0 and infinity, alpha and beta are strictly between 0 and infinity, and T and S are real number, such that we have actually this condition: alpha minus T is equal to beta minus S. Then this HPQ alpha norm of fractional derivative of order T of function f is comparable to the norm HPQ beta mixed norm of fractional derivative of order S of function f. So we have this relation. Under this condition, we have that HPQ alpha T is the same space as HPQ beta S. So nothing changes if we add the same number to these two parameters alpha and T. So here we add beta minus alpha, and beta minus alpha is the same as S minus T. So here down we add S minus T. Weighted Bergman space, so P is strictly between 0 and infinity, alpha greater than -1. We use this notation AP alpha for the weighted Bergman space. And of course, that is the space of all holomorphic functions for which this LP norm is finite. We have this weight 1 minus square of modulus of Z to the alpha, and we have this normalization alpha plus 1 over P. And also here, dm is a standard Euclidean area measure in the complex plane. So this is dm, and if alpha is equal to 0, then we have a standard Bergman or unweighted spaces. It is very easy to check that weighted Bergman space AP alpha is actually mixed norm space H with these coefficients P, P, and alpha plus 1 over P. And also we have a weighted Dirichlet space dP alpha. So this is the space of all function f holomorphic in the unit disk D, for which first derivative or equivalently first fractional derivative of function f belongs to this weighted Bergman space with the same parameters p and alpha. And so we can write that Dirichlet space dp alpha is actually from this d to the -1 of weighted Bergman space, and that is d to the -1 of this mixed norm space. And this is exactly the generalized mixed norm space with these parameters p, p alpha plus 1 over p and down 1. And something briefly related to this Hardy-Bloch and Besov spaces. So Hardy-Bloch space BPQ, P and Q are again between 0 and infinity, and also they can be equal to infinity. So the space Hardy-Bloch space BPQ is actually generalized mixed norm space HPQ11. And in the case when P and Q are equal to infinity, we have standard Bloch space B. So Bloch space B is actually this space H infinity infinity 1 1. And in this context, Bloch space is the space of all functions f holomorphic in the unit disk D, for which this first fractional derivative of f, or again, equivalently, the first derivative of f belongs to this mixed norm space. And from the definition of this mixed norm space, we have the following. So block space B is the space of all holomorphic function f, for which this modulus of first derivative of f is actually a big O of this quantity 1 over 1 minus square modulus of z. And also we have Besov spaces BP, where P is strictly between 0 and infinity, and in some books analytic Besov spaces BP. Besov space BP is actually generalized mixed norm space H PP1 1 plus 1 over P. So this is Besov space BP, and when P is strictly between 1 and infinity, we can write the following. So this is Besov space, and nothing changes if we add the same number to these two parameters 1 and 1 plus 1 over P, and we can add a minus 1 over P. So we obtain this generalized mixed norm space, and also here 1 minus 1 over P is strictly positive, since P is greater than 1. So this is d to the minus 1 of this mixed norm space. But this mixed norm space, H PP 1 minus 1 over P, is actually a weighted Bergman space A with parameters P and P minus 2. In this case, when P is strictly between 1 and infinity, we have that Besov space BP is actually the space of all functions f holomorphic in the unit disk, for which first fractional derivative or equivalently first derivative function f belongs to this weighted Bergman space A P minus 2. So this is a standard definition of analytic Besov space BP in the case when P is greater than 1. And finally, we are going to some results related to Hilbert matrix. Actually, everything started with this very nice and very important paper from 2000 by Siskakis and his student Diamantopoulos at that time, I think. For the first time, they considered the action of the Hilbert matrix on Hardy spaces. For the first time, someone considered the action of the Hilbert matrix on some spaces of holomorphic functions in the unit disk. And they obtained this result. Hilbert matrix H is bounded on Hardy space H P if and only if P is strictly between 1 and infinity. And also, very important, they obtain the following integral representation of the Hilbert matrix. So we have this basic integral representation of the Hilbert matrix, and by using chains of variables and after some calculations, we have this second one, integral representation of Hilbert matrix, more complicated, but they use this second one representation to provide the upper bound of the norm of the Hilbert matrix H on Hardy space HP, but only in the case when P is greater or equal than 2. So they obtained this upper bound given by this quantity, again, pi over sinus pi over P. So they also proposed the conjecture that this quantity is exact norm of the Hilbert matrix on the Hardy space HP. And in the remaining case, when P is between 1 and 2, they obtain this less precise upper bound. And this problem, this conjecture, was completely solved in 2008 by Dostanic, Jevtic, and Vukotic. And they proved that in the whole range, when P is strictly between 1 and infinity, the norm of the Hilbert matrix H on the Hardy space HP is exactly equal to pi over sinus pi over P. In this theorem, they used theory of Henkel matrices, and the well-known fact related to the norm of Riesz projection on Hardy spaces. The norm of the Riesz projection on Hardy space HP is equal to 1 over sinus pi over P. And that is a famous result by Holomorphic and Verbitsky from 2000. So in this paper, they proved that the norm of the Hilbert matrix H on the Hardy space HP is actually equal to pi times the norm of Riesz projection on the Hardy space HP. So they obtained this connection between Hilbert matrix and Riesz projection on Hardy space. Hilbert matrix on the Bergman spaces, first slide. Diamantopoulos in 2004, he obtained this result. Hilbert matrix H is bounded on Bergman space AP if and only if P is between 2 and infinity. And again, by using the second one integral representation, he found this upper bound, pi over sinus 2 pi over P. And in the case when P is greater or equal than 4. And also, again, he proposed conjecture that this upper bound is the norm of the Hilbert matrix on the Bergman space AP. Again, in the remaining case, when P is between 2 and 4, he obtained this less precise upper bound. And in the same paper from 2008, when P, so we have this theorem from that paper, when P is greater or equal than 4, then this quantity, pi over sinus 2 pi over P, is the norm of the Hilbert matrix on Bergman space AP. And after that, we have the conjecture that this quantity is also the norm in the remaining case, in the remaining interval, when P is strictly between 2 and 4. And recently, we proved that conjecture. So in the remaining case, when P is between 2 and 4, this is again the norm of the Hilbert matrix on the Bergman space AP. And here I will skip the proof, which is technically complicated, and I only say that we base our method on one partially new way to use monotonicity of integral means and reduce the conjecture to some inequality related to beta function. Namely, we proved this inequality. So here we have a beta function with these coefficients 2 over pi and 1 minus 2 over pi. So this is exactly this quantity, pi over sinus 2 pi over P. And of course, P is between 2 and 4. And S is actually any number between 0 and 1. And also we have this, this function C. So integral from 0 to 1 of this function C is equal to this, this beta function. And we use a Stern theorem from classical theory of polynomials. And in general, the use of Stern theorem is technically complicated. Stern theorem actually expresses the number of distinct real roots of some polynomial P located in some given interval. And also in this paper, we use hypergeometric functions, but very recently, Lindström, Mihkinen, and Wickman in 2019, they completely remove Stern theorem from the proof of this inequality. So they provided a partially new and simplified proof of this inequality. And now I'm going to Hilbert matrix on generalized mixed norm spaces. So in 2012, Lanucha, Novak, and Pavlovic, among other things in their paper, they proved that Hilbert matrix H is bounded on this weighted Hardy space, H P infinity alpha, if and only if alpha plus 1 over P is less than 1. And also in 2014, Galanopoulos, Girella, Pelaez, and Siskakis. Actually, in this paper, they considered Hilbert matrix in more general settings, and they obtained many important results related to generalized Hilbert matrix. And also they obtained the following results related to classical Hilbert matrix. So if alpha plus 2 is between 1 and P, then Hilbert matrix H is bounded on this weighted Bergman space, AP alpha. And we do not have another implication here. So also if P is greater than 1 and alpha between P minus 2 and P minus 1, then H is bounded on Dirichlet spaces, Dirichlet space dP alpha. So after this paper, we have the following problem. Can you give a complete characterization of the boundedness of the Hilbert matrix H on weighted Bergman spaces AP alpha or on the weighted Dirichlet spaces dP alpha? And as you have seen, we have before this weighted Bergman space AP alpha is actually this mixed norm space, and this weighted Dirichlet space dP alpha is this generalized mixed norm space. So we have the problem in more general context. Characterize the boundedness of the Hilbert matrix H on generalized mixed norm spaces HPQ alpha T. So we solved this problem recently, and we obtained this very simple condition. So the Hilbert matrix H is bounded on generalized mixed norm space HPQ alpha T if and only if this quantity is between 0 and 1. So this is very simple condition, and this quantity 1 over P plus alpha minus T does not depend of this parameter Q, which is interesting. So for example, if we have a weighted Hardy space HP infinity alpha, then this quantity is equal to 1 over P plus alpha. And 1 over P plus alpha is always positive in the context of weighted Hardy space. So we obtain that Hilbert matrix H is bounded on weighted Hardy space H P infinity alpha if and only if 1 over P plus alpha is strictly less than 1. So this is a result from 2012 by Lanucha, Novak, and Pavlovic. And also we have the following consequences. First, we obtain this, this result. Hilbert matrix H is bounded on weighted Bergman space AP alpha if and only if alpha plus 2 is between 1 and P. Now we have this if and only if. And also we obtain the following interesting characterization of the boundedness of the Hilbert matrix on weighted Dirichlet space dP alpha. So we have this condition now. Maximum of this two number minus 1 and P minus 2 is less than alpha is less than 2 times P minus 2. Also, for example, in the case of Hardy-Bloch spaces, HPQ11, and in this case, this quantity is equal to 1 over P. So Hilbert matrix H is bounded on Hardy-Bloch space BPQ if and only if 1 over P is between 0 and 1. So we have this condition, P is between 1 and infinity, which is the same condition. Next, for block space B, this quantity is equal to 0. So Hilbert matrix H is unbounded on block space, and for the Besov space BP, Hilbert matrix is again unbounded. So for the Besov space BP, this quantity is equal to 0 again. And now we have Hilbert matrix on weighted Bergman spaces. So this is probably the most important part of this talk, with some open problems. And so we have this Hilbert matrix H is bounded on the weighted Bergman space AP alpha if and only if alpha plus 2 is between 1 and P. So someone can ask, what is the norm of the Hilbert matrix H on this space AP alpha? And we have this result for all P greater than alpha plus 2 in all range of P. We have this lower bound for the norm of the Hilbert matrix H on the weighted Bergman space AP alpha. And I will give a proof of this theorem, only sketch without calculations. So let gamma be between 1 and alpha plus 2, and let f gamma of z is the following function in the unit disk D. So 1 minus z to the minus gamma over P. And after some work, after some calculations, we have that norm, weighted Bergman space norm of this function f gamma to the P is actually this hypergeometric function. And this is the standard Gauss hypergeometric function with these coefficients gamma over 2, alpha plus 2 to the point 1. And also by using the first integral representation of the Hilbert matrix, we obtain that the image of this function f gamma with the Hilbert matrix H is given by this product of beta function with coefficients 1 minus gamma over P, and again hypergeometric function, this standard hypergeometric function with coefficients 1, 2 minus gamma over P, the point Z. And based on these formulas, we have the following. So we have, based on previous formulas, norm, weighted Bergman space norm of this function f gamma is finite. So this function f gamma belongs to this weighted Bergman space. And also this limit of these norms of functions f gamma is equal to infinity when gamma goes to alpha plus 2. And also we have the following representation. H of phi of gamma is actually this quantity, pi over sinus pi gamma over P times f gamma plus g gamma. For some function g gamma, and also we have that the norm that these norms of functions g gamma are bounded. So this supremum is finite when gamma is between 1 and alpha plus 2. And then the norm of the Hilbert matrix H on the weighted Bergman space AP alpha is of course greater than this quantity. And by using triangle inequality, this is greater than this quantity. So this is the quantity on the right side. And letting gamma goes to alpha plus 2, here this quotient goes to 0. since these norms of this function f gamma goes to infinity, and these norms of function g gamma are bounded from above. So we obtain this lower bound of the norm of the Hilbert matrix on the weighted Bergman space AP alpha. And this completes the proof. And also, we proposed the conjecture that this quantity pi over sinus alpha plus 2 pi over p is exactly the norm of the Hilbert matrix on this weighted Bergman space AP alpha in the whole range when p is greater than alpha plus 2. So we have that this quantity is lower bound, and it is enough to prove that this quantity is actually also upper bound for this norm. When alpha is equal to 0, then we have a case of standard Bergman space. Then then this quantity becomes pi over sinus 2 pi over p. And when alpha goes to the -1, then this quantity becomes pi over sinus pi over p, and these weighted Bergman spaces AP alpha become a Hardy space HP. So also when alpha goes to the -1, we have the case of the Hardy space HP, and we prove that this is upper bound for this norm in the case when alpha is greater than 0 and p greater or equal than 2 times alpha plus 2. So the conjecture is actually solved in this case. And also the conjecture is solved in the case when alpha is equal to 0 in the case of classical Bergman spaces AP. And after this, we have two unsolved cases when alpha is greater than 0 and p between alpha plus 2 and 2 times alpha plus 2 in the remaining interval. And this probably a much harder case when alpha is negative in the whole range when p is greater than alpha plus 2. And also recently, Lindström, Mihkinen, and Wickman, 2020, they solved conjecture in the case when alpha is greater than 0. So in this case, on this interval, when p is less than 2 times alpha plus 2, and p greater or equal than this quantity. And also, we have the next result. So again, in this case, when alpha is greater than 0 and p on this interval with endpoints alpha plus 2 and 2 times alpha plus 2, again, we use a method based on the monotonicity of integral means. And after some work, it turns out that it's useful to know when the following function, phi, given by this relation, is positive on the interval from alpha plus 2 to 2 times alpha plus 2. And it is easy to check that this function phi is increasing function on this interval, and on the left endpoint function phi is negative, and on the right endpoint function phi is positive. So this means that function phi has a unique 0, alpha 0 on this interval. And also on this interval from alpha plus 2 to alpha 0, function phi is negative, and on the remaining interval from alpha 0 to 2 times alpha plus 2, function phi is positive. And we have this result, again, in the case when alpha is greater than 0. So if p is between alpha 0 and 2 times alpha plus 2, we have this equality, so we have positive solution of conjecture. Something about location of this of the number alpha 0. So let beta be this number, and gamma, this from the result of Lindstrom, Mikinen, and Wickman. Here we have minus alpha plus 2, and here minus 1/2, that is 0.5 times alpha plus 2. And also let delta be this number, minus square root of 2 minus 1/2 times alpha plus 2. And this is approximately, I think, 0.914. So this number is very close to beta, and of course beta is smaller than delta, and delta is smaller than gamma. And it is interesting that alpha 0 is between beta and delta. So it can be checked that function phi of beta is less than 0, and function psi of delta is greater than 0. So on the interval with these two endpoints, alpha plus 2 and 2 times alpha plus 2, we have somewhere alpha 0, this point alpha 0. And on this part, from alpha 0 to 2 times alpha plus 2, we have a positive solution of conjecture. And on the remaining interval, on this bigger interval, we do not have solution of conjecture. So the open problem is from alpha plus 2 to alpha 0 in the case when alpha is greater than 0. And alpha 0 is between delta and beta. And of course, gamma is bigger than delta. So on this interval, from gamma to 2 times alpha plus 2, this is a result of Lindstrom, Mikinen, and Wickman. And also, the problematic part is interval from alpha plus 2 to alpha 0, but on this subinterval from alpha plus 2 to beta, we have one partial result. So from the same paper, we have that in the case when alpha is greater than 0 and p between alpha plus 2 and beta, but suppose that the following extra inequality holds, extra condition labeled with star. So if we suppose that this inequality holds, here again we have beta function with these coefficients alpha plus 2 over p and 1 minus alpha plus 2 over p. So this is quantity pi over sinus alpha plus 2 pi over p. And here psi is this function. So integral from 0 to 1 of function psi is again this beta function. And also we have this function psi. So if we suppose that this inequality holds, then we have a solution of conjecture. And it is interesting that this inequality is not always satisfied under these conditions. So, for example, if we have that alpha is equal to 1, in that case, we have actually that beta is approximately 5.449 and alpha 0 is 5.487. And if we choose that p is equal to 4.4, so p is between alpha plus 2 and beta, then left side of the star minus right side is positive. So inequality star is not satisfied, but in some cases we can use the previous theorem. For example, if alpha again is equal to 1 and p is equal to 5.2, again p is between alpha plus 2 and beta. then left side minus right side is negative, so we can use that theorem. And that is all in the case when alpha is greater than 0. In the remaining unsolved case, when alpha is negative, in the all range, when p is greater than alpha plus 2, we only have the following result with this less precise upper bounds. So when p is greater or equal than 2 times alpha plus 2, we have this upper bound, and in the remaining case, we also have this less precise upper bound. And also, I can say something very briefly related to generalized Hilbert matrix. So Hilbert matrix H is this matrix, and this is actually the same as integral from 0 to 1 t to the n plus k dt. So this is 1 over n plus k plus 1. And let me be a positive Boban measure on this interval from 0 to 1. Then the generalized Hilbert matrix H me is this infinite matrix, whose entries are given by these integrals from 0 to 1, t to the n plus k, with this measure me now. So if me is a Lebesgue measure on this interval, we obtain the standard Hilbert matrix H. And there are many important and very nice results related to this generalized Hilbert matrix. And I list some of them. So we have this paper, Hatzifontas, Givela, Pelaez, 2014, on the Hardy spaces. Galanopoulos, Pelaez, 2014, on Hardy and Bergman spaces. Givela, Merchant, on some spaces of analytic functions. Again, Givela, Merchant, on some conformally invariant spaces. And this very nice paper from 2019, Givela, Merchant, on Hardy space H1 and Dirichlet spaces. Merchant on Lipschitz spaces, and this paper on spaces that are close to the Hardy space H1 and to the space BMO A. And that is all. And thank you. Thank you.
So thank you so much. Glad to see that the Hilbert matrix has been explored further. Does anybody have, first of all, are you willing to share your slides with us? Can you post that in the chat?
Okay, I will try now to share. Okay.
Perfect. Does anybody have any comments or questions?
Bill, if you allow me, I would like to say a few things.
Okay.
Hi. Hi, nice talk, first of all. Nice material. I'd like to just point out one thing. We might have misled everyone by working at it some time ago, mainly on the norm question. I think it's also an important broader question to study the spectrum. If you study the spectrum of this operator, then it reveals many more things, and in particular, you get the norm. So roughly speaking, I'd like to point out to you a recent reference, which I don't know, it doesn't seem that you have cited it. It's a work by Silberman. He's an older mathematician, from the book by, for example, by Becher and Silberman on Toplitz's operators. So it's a 2021 paper, I believe, in integral equations and operator theory. He can actually compute the spectrum of the Hilbert matrix on Hardy spaces and sequence spaces such as LP spaces. So this is probably worth looking into. And essentially what happens, we've been working on this. When I say we, I mean Siskakis, who is here, and Aleman for several years. And we actually have obtained some results in parallel. And I don't know when we'll finish writing up the paper on this. Perhaps by the time of my talk, which is in 3 months, in the same semester, we might have a little more, but written up. But roughly speaking, when you look at the spectrum of the Magnus, Wilhelm Magnus showed in his early paper in 1950 that if you consider your Hilbert matrix on the L2 sequence space, so the Hardy space H2, it's an operator with a purely continuous spectrum, no eigenvalues, no residual spectrum. And he determined the spectrum to be the interval 0 pi. And that's the reason why the norm is pi in Hilbert's inequality, right? So that's the explanation for the H2 case. But you can actually see that the spectrum is often something a little thicker in these spaces, like the ones you consider. It should look like more or less like an ice cream cone with the vertex at the origin, and the place where we start eating the ice cream is the most distant point from the origin. So this tells you how big the norm is. Roughly speaking, because you have the spectral radius. So that's, I think, what this number that you have frequently, pi over sine 2 pi over p and similar ones, actually represents. So we have been able to determine this, but so has Silberman. And so results can be given. You have to employ other techniques, but one can actually determine the entire spectrum and its part. Sometimes you can have the point spectrum, often you don't. The spectrum can be thinner or thicker, but that tells you why the number is the number you get. So there is, I think there is more territory you can explore, and I would encourage you to do it, because I don't know when we'll finish writing up this paper, and there is probably more to be done in different contexts and spaces. Our technique does not quite cover everything we would like to compute, so there is room to do more work. Yes.
Thank you very much for that information.
Yeah, I don't want to talk more, so that's
okay,
all.
But maybe just as a private email, if you can send me some references about the spectrum of the Hilbert matrix.
Oh, sure, yeah, absolutely, absolutely.
Are there any other comments or questions anybody wants to add here?
Yes, that is very nice about spectrum, of course.
So
I have a question. It's a very, I think, very simple question. In the Hardy space case, you say that the norm is related with the norm of the risk projection. Is it the case the same for the Bergman space?
It is very hard to give connection between the norm of the Hilbert matrix and the Bergman projection. I don't know something about that connection.
Okay, thank you.
Okay, so nothing in the chat. Anybody else have any comment? It was a very engaging talk. Lots to think about. So with that,
I can say something, sorry, about this last question, if I may. In the Hardy space case, the norm of the Hilbert matrix is exactly the norm of the Riesz projection times pi. If I'm not mistaken, that's explained in the paper by Dostanic and Jeftic and myself. In the Bergman space case, this is very difficult because the norm of the projection, say, is very difficult to compute. So I think you're right. It's a difficult question. So I'm not sure if a clear connection can be established yet. Sorry.
okay, any last minute thoughts? All right, so with that, let's heartily thank our speaker again. So he gave us a lot to think about and a lot of engagement. So thank you.
Thank you very much.
I think